It's a real pleasure to introduce our own Alex Lubotzky. I'm using the expression our own because officially he's an alumnus. I remember having the pleasure maybe 10 years ago of giving Alex an honorary degree. Now, for all of you students here, you should know honorary degrees are really different than regular degrees. Regular degrees you have to work for. Honorary degrees, it means that, you know, you're a good friend of ours. So it's a very great pleasure to introduce our good friend, Alex, who will be giving the colloquium today.
Yeah, thank you. Thank you very much. It's really pleasure to be once again in Chicago, though I really was planning to be. In fact, before, when I agreed to come here, I was supposed to visit you like a year and a half ago, and then for family reasons I had to cancel, and I kind of swear to myself that I will not go out from Princeton except of Chicago, and unfortunately it doesn't seem like even this is going to happen. So I'm taking a rain check to come at some point to really come to Chicago. Anyway, we'll do it now in the best what we can do. I would like to talk about this subject of stability and unapproximated group, which is somewhat will come up related to high-dimensional expander. I will explain everything. This is a colloquium talk, and you're not expected to know any of this notion. So a group gamma is called residually finite if for every non-trivial element G in the group, there exists an homomorphism from gamma to a finite group F such that phi of G is not one. Namely, the homomorphism, the set of all possible homomorphisms from gamma to finite groups separate the points of F, because if you can separate everything from the identity, then you easily, you see that you can separate any two elements from each other. For example, if you want to think about gamma being, say, finitely generated, which is really our main interest or the only interest all the time, then if you take the Cayley graph of gamma, then you can see that locally the Cayley graph of gamma looks like a Cayley graph of a finite group. And this is a long tradition in group theory, and I guess not only in group theory. You have a complicated object like an infinite group gamma, you want to study it via objects which are somewhat simpler, and finite groups are, at least to some extent, are simpler to understand than infinite groups. And an equivalent way to say it, because every finite group can be embedded into the symmetric group, this is known as a Cayley theorem, simply by letting the finite group acting on itself, let's say from the left, then it's equivalent to say that for every G in gamma, we have an homomorphism from gamma to the symmetric group, so that phi of G is not one. And you can even see that in this type of homomorphism obtained from the Cayley graph, from the Cayley theorem, the action of G, if it's non-trivial, then it fixes no element. It really moves all the elements. Anyway, there are many groups which are residually finite. For example, every finitely generated linear group is residually finite. The automorphism group of the free group is residually finite. The mapping class group is residually finite. I guess that in any other place I have to say what is the mapping class group, but in Chicago, probably even the secretaries know what is the mapping class group. And those who don't, ask Benson. But of course, there are groups, including finitely generated groups, which are not residually finite. For example, simple groups. Something like 30, maybe by now it's already 40 years ago, Gromov came with the definition of a sofic group, or I should say probably Gromov and Benji Weiss. And they define a group. Well, the original definition was maybe slightly different, but I want to put in a more general framework So I really want to define it in this way, which is equivalent to the original definition. And a group is sofic if there exist maps from from gamma to the symmetric group. Now, stress, maps. When I say now a map, I don't mean an homomorphism, just functions from gamma to the symmetric group, Sn, such that for every G and H in gamma, the limit of the distance, we'll say exactly what we mean by distance, the limit of the distance between phi n of gh and phi n of g, phi n of h, the limit when n goes to infinity is 0. Namely, each one of these maps, phi n individually is not an homomorphism, but they are kind of asymptotic homomorphism. They kind of, if you think of them as a kind of a convergent set, it converges to a kind of homomorphism, which of course do not really exist here in that level. And okay, so this is the condition of being asymptotic homomorphism, but you want also that that these maps will separate the point, right? Residually finite, you say you have homomorphism which separate the point. Then this means that every G, which is not one, the lim sub, or the limit doesn't really matter here. The distance between phi n of G and the identity is bounded away from 0. So, you know, the element is not really going eventually to the identity. Now, what is the matrix? The matrix, you can pick your own. But in this, in the symmetric group, and we'll see when we're going to generalize that we can take various different matrices of various different groups. Here we are talking about the normalized Hamming distance, which means that Dn of between two permutation tau and sigma is 1 over n, the number of I between 1 and n, such that, oops, the letter sigma is missing, so that sigma should be here sigma. Sigma of n is not equal to tau of sigma of I should be not equal to tau of I. I'm sorry, I should really correct this, but I don't know how to do it now online. But it's simply said the distance between two permutation is 1 over n. In how many entries they are different, just, you know, very natural. Now, it's easy to see that residually finite groups are sofic. It's a little exercise, but also not difficult to see if you know the definition of amenable group, that amenable groups are also sofic. But sofic is a generalization of both. There are groups which are residually finite and which are not residually finite and non-amenable, and still they are sofic. The name sofic actually comes from the Hebrew word sofi. Benji Weiss was the one who gave the name. In Hebrew, sofi means finite or finitary, and he told me that it was, you know, he really thought that maybe he should call it finitary or something like that, but there are too many words like that in mathematics, finitary. So he took the Hebrew word sofi, but he didn't want it to sound like Hebrew, so he said sofic instead of sofi, and he picked up, and everyone now call it sofic. And even if they don't know what the origin, like a year ago, Benji Weiss gave a talk in Israel, and he gave a talk to students, like undergraduate student, in kind of a club, undergraduate club, and the title was, in Hebrew, tele groups. I read the abstract, and it was clear to me that he's going to talk about sofic groups. So I asked him, why you call it tele? He said, well, if I give a talk in English, I call it in Hebrew. If I give a talk in Hebrew, I should call it in a Old Greek. And apparently, in Old Greek, sofi, finite is tele, so that's the name he gave it in Hebrew. Anyway, it's a major open problem, maybe one of the most outstanding problem in modern kind of infinite group theory. Are there non-sofic groups? Whether every group is sofic. This was, when it started, it was kind of a curiosity question, but there are more and more theorems which start like that. If gamma is sofic, then Kaplansky conjecture is correct. You know, if this is this, which means that we know to prove various results which were open for a number of years are known now to be correct if the group is sofic. And so, of course, we want to know if every group is sofic, but I have to admit that once people prove more and more results on sofic group, you start to believe that it's not true that every group is sofic, because we don't really believe that all groups satisfy some. Usually you say that if all groups satisfy a property, it's either trivial or not interesting. So somehow I think that the common wisdom now, what people believe, that there are non-sofic groups, but it's widely open. There are some candidates that people propose. You can easily propose candidates, but nobody knows how to handle that. We are not going to solve it, but maybe we'll get a little insight about this problem also today. Anyway, what we know when in mathematics, when we don't know to solve, we generalize. So let's generalize and look at the following. Let Gothic G be a family of groups with bi-invariant matrix. Gn and Dn will be a family of groups, like before the symmetric group and the normalized Hamming matrix. And then we will say that a group gamma is G approximated if there exist maps from gamma to Gn satisfying, one, they are asymptotic homomorphisms. So you remember, what does it mean to be an asymptotic homomorphism? It means that eventually you look like an homomorphism, right? And also they separate the point. It's exactly satisfying the condition one and two in the previous slides. You know, for every G and H in gamma, the limit of the distance between phi n GH and phi n G, phi n H goes to 0. And for every individual element, which is not one, the image is kind of bounded away from the identity. So you can approximate gamma by the family group Gn if you have such maps, which again, I stress, these maps are not homomorphism, but only kind of almost homomorphism, asymptotic homomorphism. Let me talk about the main examples that we are really interested in. So first of all, the symmetric group with the normalized Hamming distance that we talk about, and this now to be G approximated with respect to this family exactly means to be sofic. That's equivalent. In all other examples, you will see I'm going to take the same groups. The groups, the Gn will be always the unitary group, U and the group of unitary matrices. The distance is going to be defined by some norm on the n by n matrices. And different norms will lead to different matrix, and different matrix will lead to different classes of groups and different definition of what does it mean to be G approximated. Let me stress this, and I will illustrate it in a minute. So let's just, for notation, if A is any n by n complex matrix, then it's easy to see that A star A is a normal matrix. Every normal matrix is diagonal. Moreover, if you think about it for a second, you see that all the eigenvalue here must of A star A must be real and non-negative. So we can really take the square root of this matrix. The square root of this matrix, we will denote it as the absolute value of the matrix A. So this is also an n by n matrix. Now I'm going to define you several different norms on the n by n matrices. And each one of them, once you have the norm, you have a matrix on the unitary group, which is the distance between G and H is the norm of G minus H. But each time, each example here will be with a different norm. So the first one, again, the groups is the unitary group. The matrix is the so-called Hilbert-Schmidt matrix, which is obtained from the Hilbert-Schmidt norm. What is the Hilbert-Schmidt norm? This is square root of 1 over n, the trace of the absolute value of A squared. If you think about it, is like basically the trace of A squared is like, in some sense, taking the absolute value of the eigenvalues of A, but we normalize it by dividing it by 1 over square root of n, or 1 over n, and then square root. This is called the Hilbert-Schmidt norm. Now, groups which are G-approximated with respect to this family of groups and these specific matrix are called in the literature hyperlinear groups. It's actually a pretty bad name because linear groups are always hyperlinear, while hyperlinear are not always linear. And it sounds like hyperlinear means more than linear. So it really means less than linear. Some people started to call it also cones embedded groups because it's a well-known open problem due to Allen cones whether every group is hyperlinear, whether every group is really G-approximated like that. There is not directly progress on that problem, but some of you may be aware that there is a kind of a breakthrough recently of using some ideas from quantum computation to dispute the so-called cones embedding problem, which is something which is very related, though it's really for algebras and not for groups. So this problem is still very much open. Usually, I'm going to define you several groups, families of groups which are approximated, and there are no connection. Here there is a connection in one direction. Every sofic group is hyperlinear, but we don't know and we don't expect that every hyperlinear is sofic. Okay, so let's take a few more examples. Again, the examples are maybe boring now, but I want to stress a point here. We'll take exactly the same family of groups UN, but this time we'll take the norm, the metric to be the, sometimes it's called the Frobenius norm, which is, again, you use the same thing. You take the trace of the absolute value of A square root of it. You only don't normalize. You don't divide by 1 over n. That's all. It's just a renormalization of the Hilbert-Schmidt norm. But I want to stress now something that let me take a minute so everyone can digest this. You see, clearly the Hilbert-Schmidt norm, the Hilbert-Schmidt matrix is always less or equal than the Frobenius matrix. But assume you know that the group is Frobenius approximated. You cannot deduce that it is Hilbert-Schmidt approximated. Why? You have maps which are asymptotic homomorphism with respect to Frobenius. So they are indeed asymptotic homomorphism with respect to the Hilbert-Schmidt, because the Hilbert-Schmidt is even smaller. But the separation works in the opposite direction. Maybe these asymptotic homomorphisms separate the points for the Frobenius, but do not separate the point with the Hilbert-Schmidt. In the opposite direction, assume you have asymptotic separating maps for the Hilbert-Schmidt, then you know that they separate also for the Frobenius, but maybe they are not asymptotic homomorphism for the Frobenius. So these are entirely different problems. The question whether all groups are Frobenius approximated, and the question whether all groups are Hilbert-Schmidt approximated, are hyperlinear, are entirely different problem. Benson. Yeah.
The separating property, though, that doesn't have to do with the metric, right?
No, it has. It has, because you see what happens, you take the distance between the images and the identity. If there is a matrix which is smaller, maybe it does not separate. The bigger matrix may separate. You see, the Frobenius may be separate, but the Hilbert-Schmidt converges to at the same time to one. If the two matrices are kind of Lifshitz equivalent, you know, kind of, then it's the same. But if one goes to zero without that, it's a different point. But maybe I can ask you, I can unmute, and I ask you which problem you think is easier to solve, the Frobenius approximated or the Hilbert-Schmidt?
Yeah, hard to tell.
Hard to tell. They look like all the same, right? Okay, so stay tuned. It turns out that there is a difference. Okay, but let's continue. Now fix any p between 1 and infinity, and define the norm now to be, sometimes it's called the Schachten P norm. It's a kind of an LP norm of the eigenvalue. You take the absolute value of A to the P, you take the trace of it, and then you take all this to the pth root of all this. And so the p equal 2 is exactly the previous example of Frobenius, but you have infinitely many different norms here, and infinitely many different classes of groups, and we cannot relate them to each other. We don't know if something is P approximated, is it also Q approximated, or vice versa. It's exactly the same problem. We don't know how to relate them. And we can also take another example, which there are more examples, but this one I think will be the last one for today. And this is the operator norm that some people consider it as the P equal infinity in this family, in these examples of number 4. And here you simply take the norm to be the operator norm. And here, groups which are approximated by operator in the operator norm are called in the classical literature for some reason. It came up in a C-star theory, and they called MF. And Kirchberg actually even suggested that every group is MF approximated. I don't think many people still believe that. Anyway, as you can see, there are uncountably many independent open problems. Like, you know, for each P, you can ask that it's a different problem. The good news is that we can solve some of them. So the first theorem, which is in a way what started the kind of the breakthrough in this type of questions, is the following. It's a joint work with Marcus de Chiffre, Lev Glebsky, and Andreas Thom. There exist finitely presented non-Frobenius approximate groups. So Benson, this answer, you know, at least this one we know to solve, the other one we don't. Shortly after that, and you will understand why, with his R Oppenheim, we managed to solve it for all P between 1 and infinity. Moreover, we can even say that there exists one finitely presented group which is not p-approximated for any p between 1 and infinity. The same group which is not approximated to all of them. But it's a little bit of a cheating. I will say something about that if you will. So out of this uncountably many open problem, only 4 were left. Sofic, hyperlinear, MF, and the case of p equal 1. But to be honest, I'm very happy that we solve uncountably many open problems. I would trade them all from one of these, at least one of the first 3, which are famous classical open problems. But somebody said something?
Yes, I did.
Yeah.
Just before we go much further, which of these questions are geometric? Are any of these geometric problems about the group?
To be honest, I don't know, Shmuel. I wanted to start to talk with you exactly in order to milk out of you if this can be expressed in some way, in some geometric, these bundles which are almost.
Right, because of all the things that you mentioned so far, only the amenability was a geometric property. Like property B is not, various things that have been coming up, they're not so geometric.
Right, I don't know.
Thinking about the example, because I heard your talks, another talk of yours, I realized, it's a non-geometric phenomenon.
Yeah, I will. Up to now, I talk about approximation. In a minute, I'm going to connect it to stability, and stability is something which you start to see a little bit of geometry.
Okay.
Anyway, the approximated is like residually finite. Residually finite is a geometric property. Of course, in some sense, it's geometric. If this is a fundamental group of something, then you have finite sheeted cover, which kind of converge to the universal cover, you can say.
Right, but it's also not geometric in the sense of geometric group theory. I presume someone who's listening would give me examples of 2 quasi-isometric groups, one of which is residually finite and one of which isn't. And yes, of course, the Deligne construction.
Right. Okay, at this point, that's actually you suggested now a problem. Okay, good. I will think myself, I'll give to a student. Now that we know to produce say Frobenius approximated groups, can we find quasi-isometric groups that one of them is Frobenius approximated and the other one is not? That's a good question, which I don't see the answer right away, but I will remember that. I have many students who want problems. So.
Okay, anyway, sorry for
sounds like a good one.
Yeah.
No, it's okay. It's with pleasure. As many questions, it makes it lovely. It's so difficult to talk to and not see faces that I am happy whenever somebody is talking. Please talk without asking permission. Just unmute yourself and talk. Okay. For the proof, I want to introduce something which is not completely different, but a different new subject. Even if you missed something in the first subject, I'm starting in some sense from scratch and I will connect them. And this is the story of stability. What we call it stability. Again, now we should warn the secretaries at the math department because I know they hear a lot of stability also from Benson, but it's a different kind of stability. Though your student, Ned Froman, who is here, suggested something even during the seminar today that maybe can start to connect the two. But it's a different type of stability. So let G, Gothic G, be again a family of groups, each one of them with a bi-invariant matrix. And gamma, some other group, usually finitely generated. We say that gamma is G stable if whenever we have maps as before, phi n from gamma to gn, which are asymptotic homomorphisms. So you have maps which are not really homomorphism, but behave eventually like more and more like homomorphism. They are really just a small deformation of true homomorphism. Namely, there exists homomorphism psi n from gamma to g, true homomorphism, such that for every g, the distance between phi n of g and phi n psi n of g, and phi n of g goes to 0. It's clear that if you have this property, then phi n are asymptotic homomorphism. This subject, not exactly in this language, is very classical, originated in mathematical physics. People have studied the following type of a problem, and if you think about it, you see that they're equivalent. Take two matrices which almost commute. And you can kind of imagine, if you know a little bit of physics, or even if you don't, you know much like me, then you can imagine why this is a kind of a problem of interest in mathematical physics. You have two matrices which almost commute. Can you deform them a bit to get matrices which truly commute? I always like, if I give a talk, a full talk about stability, I like to bring the title of two papers in the literature. One of them says, every nearly commuting matrices are near commuting matrices. And one of them says, not every nearly commuting matrices are near commuting matrices. Both papers are correct, and there is no fundamental contradiction in mathematics. It's simply that each one of them is talking on a different metric. And you can ask also this question in various categories, in complex matrices, in self-adjoint matrices, and unitary, maybe the two commuting are unitary, maybe I can correct them, but not within the unitary group. And there are dozens of papers around it. If you think about them, in a way, if you say that you can correct it, you basically say that the group Z cross Z is stable. Because if the relations of the group are almost satisfied, it really, like between you have a family of groups, you have commutators, which is closer and closer to identity. It exactly means that you can define maps which are almost homomorphism of Z cross Z. So you can think of this subject as a generalization from the commuting to more general set of equations. There is another connection that I will not elaborate, but I think I saw Osborov in the audience, if I'm not mistaken, or some from the computer scientists. What?
I was about to ask you about this connection.
Yeah, so there is a connection to the computer science testability. In fact, my interest in all these subjects started a few years ago that I saw a paper which proved that two permutations which almost commute are indeed nearby commuting permutations. Again, with the normalized amic distance and n going to infinity. In the computer science language, it basically says the following, that the problem of commutativity is testable. Testable and property testing is a big subject these days in computer science. That people want to know, I have a property of graphs. Actually, here is a problem which is of fundamental importance in error correcting codes. You have a very long code of 200,000 bits, and somebody sends you a code word, and you want to know if this is really a code word or it's very corrupted. If it's 2%, 5% corrupted, you can correct it. You have an algorithm to correct it. But if it is 40% corrupted, there is no reason to read even. So you want to read only locally. You want to read 70 random bits, and to decide, at least probabilistically, if the vector is sufficiently close to a code word that your algorithm can correct it. Think about the permuting matrices, permutation as a code inside the symmetric group cross itself. Like the subset is AB of all AB, so that AB equal BA. And somebody give you two permutation X, Y, and you have to decide if X and Y commute or very close to be commute. a theorem like that of stability tells you that this is indeed the case. And how do you check it? You will pick up 70 random i's between 1 to n. If x y of I is equal y of x of I, then this shows that, that these are almost commute, and therefore by the non-trivial theorem, they're close to commute. So in a way, this is very related to this subject. Those who will come to the seminar I'm running here in Princeton, who will come by Zoom, will hear, can hear a little bit more about that. I don't want now to elaborate, because I really want to use the rest of the time to give you kind of a sketch of the proof of theorem A, and theorem B is sort of it's coming after. Okay, but let me say something about the proof of theorem A. Okay, so theorem A, what it said that there exist non-Frobenius groups. And we want to prove there exist non-sofic groups. We want to prove there exist non-hyperlinear groups, right? Already 15 years ago, Glebsky and Riviera made the following very simple observation. They said the following: assume G is like the families before, and gamma is a finitely generated group. Assume gamma is G approximated, and at the same time, G stable, then it is residually finite. I will give you the proof. The proof is a few lines, and you know, every good lecture and even not so good lecture should contain a little proof, so I will prove this, but let's see the corollary first. It means that if you have a group which is finitely generated, G stable, and not residually finite, then it is not G approximated. So this has a potential to be a method to prove that there exists non-G approximated group, non-sofic group, non-hyperlinear group, non-Frobenius group. So the only thing you have to prove is that you have a G stable, which is not residually finite. Okay, let's see the proof first, and then we'll continue. Assume gamma is G approximated. So what does it mean is G approximated? We have a system of we have separating asymptotic homomorphism, not homomorphism, just asymptotic homomorphism phi n to Gn. That's which separate the point. That's the meaning of being G approximated. But at the same time, gamma is also G stable. This is the assumption that G approximated and G stable. It means that I can replace each one of these phi n by psi n, which is a true homomorphism. And they're very close. And now, if it's easy to see that if the phi n are separating, then the psi n also separating, which means that gamma can be separated by finitely generated linear groups, because each one of these psi n of gamma is, if you are in the symmetric group, you are already finite. If you are in UN, you are in a linear group, in the n by n matrices, but it's a finitely generated group because the group started is finitely generated. It's well known that, you remember I mentioned that at the very, very beginning that linear groups are residually finite. It's like a Chekhov play. If you have a pistol on the table at the first slide, it will appear at the very end. So this classical theorem of Malchev claiming that every linear, finitely generated linear group residually finite is crucial here, because this psi n of gamma are residually finite, so we can separate the points of gamma by homomorphism to residually finite groups. Each one of these residually finite group, I can separate each point by finite quotient, and therefore I can separate the points of gamma by finite quotients, namely gamma is residually finite. Just as simple as that. Okay, so what we want now, we just want to find a group a finitely gendered group, which is not residually finite, well, there are plenty of examples, but to prove G stability. Well, to prove G stability is easier to say than to do, but still, there is some hope. And indeed, that's what we are trying this day to develop techniques to prove stability or instability. You see, when we talk about this Z cross Z, these are non-trivial theorems, not very difficult, but what you do, you kind of take matrices, you say, I smash it a bit, they almost commute, I take this entry, I will move this entry, I will do something. But somehow if I give you a group with a very complicated presentation, it's not so easy to do it. Benson? Yeah.
I have a question. There's a group that if you take the group with two generators, A and B, where A B squared A inverse is B cubed. So it conjugates these Baumschlag solitary.
Yeah. We know a lot about them. About stability.
Is it G stable? That's what I would guess.
Yeah. So it depends on what it's for permutation. It is indeed well. Okay. Sorry. You have to take the case where this residually finite. Okay. Those cases which are residually finite are indeed permutation stable. I don't think we know it for all the other families. I don't think it's always true. I have to think about it. But for permutation, we studied them. It's a non-trivial theorem, by the way.
Okay. Just for the audience, I asked this question is because the group I said that A B squared A inverse is B cubed. It's not residually finite, and it's almost close enough to commuting. It's not, but it feels like it, like A B A inverse is, that you might hope to prove stability, because
Right.
Benson, I mean, right, that group is an amalgamated free product of free groups over free groups. Is that right? Right. So it could be that you could do the cohomology calculation.
It's okay. So Shmuel, you know too much, Shmuel, because
all right, never mind.
I didn't say yet cohomology. I didn't say it's cohomology.
Yeah, what does that have to do?
What this has to do? Okay, so here is Shmuel. Just pick up the next slides. The next slide, which was really in some sense the breakthrough. Why? Because to prove stability directly is extremely difficult. How do you prove stability? You see, I mean, the difficulty is that we are in mathematics, in group theory, we have a lot of experience working with homomorphism. Kernel, quotient, almost homomorphism. What does it mean? What is the kernel of almost homomorphism? It's not well-defined object. So here is a theorem which suddenly brings us back to more ordinary type of group theory. And it says the following. Assume that's in a way was the breakthrough which started all those results that I will tell you in a minute. Assume gamma is a finitely generated group and assume that H2 gamma V is 0 for every unitary representation of gamma on any Hilbert space V, then gamma is Frobenius stable. In the family of UN and the Frobenius matrix, it is stable. You're probably a little bit surprised what the connection of this H2 of this cohomology and stability. I will come back to that toward the end. Let me take a few minutes to show how we are using it to get Frobenius approximated group, because it's also interesting and it brings another subject. And if you want another connection with computer science, and this is Garland theory, or if you want high-dimensional expander in my title, that's exactly the story now here. That's a method. Garland method gives us plenty of examples for which A2 vanish. Here is, I will say it in big words, some of you very familiar, some of you even more than me, I believe. I saw some of the faces, but I will say something for those who are less familiar. If G is a simple p-adic Lie group. Namely, you take like SLN over the p-adic number, or the SP2G over the p-adic number of rank R. If you know what is rank, good. If not, maybe even better, think of it. Well, every such simple Lie group, you can associate with it the so-called Bruhat-Tits building. This is an infinite simplicial complex on which the Lie group acts. And the dimension of this building is the rank of G. Assume the rank is at least 2. Let gamma be a co-compact lattice. So if you take a co-compact lattice and you take the building B and you divide it by the gamma, you get just a finite simplicial complex of dimension R. And those are what we are now many of us are interested in them. They are the I-dimensional expanders, sometimes Ramanujan complexes, etc., etc. And one of their properties, which was proved by Garland, is exactly, you can think of it combinatorially. In fact, its proof is very much combinatorially, or in a group theoretic language, it says the following: if the prime P is much larger than R, the rank, then HI gamma V is equal 0 for every unitary representation and every Hilbert space and every I between 1 to R. To be honest, Garland proved it for finite dimensional. It was extended by various people. Bolman and Svetkovsky are the one who really formulated exactly what we need. Okay, so we get plenty of groups which satisfy the vanishing of H2 as we need. The problem is that all of them are linear, right? They are lattice in Lie groups, so all of them are residually finite. What we should do? We have to take R greater or equal 3 because we need I less than R. Maybe for R equal 1, there would be a chance. Some of you know that there exists this non-classical building of dimension 2, which give rise to lattices which are not linear. Maybe they are not residually finite, but they cannot help us because we need H2 to be 0. Okay, luckily, we are old enough, and some of us remember a little results of Deligne. To be honest, I never understood why he cared about that, but in 1978, Deligne showed that for some non-uniform arithmetic lattice in the symplectic group over the real numbers, for some such gamma, you can find a finite cover, central cover. There exists some gamma tilde covering gamma with a finite central kernel, and gamma tilde is not residually finite. That's good, right? Well, or maybe just historical remark. He did it only for non-uniform. Raghunathan proved it later on for some co-compact. Retroactively, this became an important theorem by the work of Toledo, who used this line of results to prove that there exists some projective complex variety whose fundamental group is non-residually finite. But frankly, at the time, I don't think this was the motivation of Deligne, and to be honest, I don't know what was his motivation. Anyway, we can imitate the work of Deligne over the p-adic numbers. I want to mention here, to give a big compliment to Dave Whitty Morris, who was a student of Bob Zimmer in Chicago, if some of you may remember, who really helped us a lot without even knowing that. He gave a talk somewhere in the work of Deligne, and he translated it to a language I couldn't understand, because I couldn't understand the paper of Deligne, and not because of the French. You know, he expressed everything in his algebraic geometry in a language which I could. On the other hand, Dave explained it in a seminar, and he's just bothered to put it on the web, and accidentally I came across And I understood. And then you can imitate the construction of Deligne. He probably could not do it at the time because you need the congruence of property, which meanwhile was proved by Rapinchuk to some of these co-compact lattices. So there is pretty much work, but it was kind of waiting for us on the shelf. And then you can prove the following. If you take the group SP2GQP and gamma and arithmetic co-compact lattice, you can do the same construction of Deligne. You can find gamma tilde, which covers gamma with a finite kernel, even central kernel, and it's not residually finite. So we are done. Why? Because it's an easy spectral sequence argument to show that if for such a group gamma H2 vanish always, it's true also for gamma tilde because Z is finite. So we have a group which is with the property we need, H2 vanish. So it is Frobenius stable. It's not residually finite. Well, let's be honest, it's not residually finite, only on the nose. You know, the intersection of the finite index subgroup of it is equal exactly to Z, which is a finite group, but it's not trivial. So it's not residually finite. And it satisfies all the conditions, and therefore it is not a Frobenius approximate. Okay,
Alex,
yeah.
what goes wrong if you you can get such examples where Z is Z with the integers, where your Z is the integers, or no?
No,
Not here.
Oh, you mean that the
central
kernel is Z,
extension.
the integers? Oh yeah, no, that doesn't go wrong, but we make it little bit maybe more the argument with the spectral sequence is
Right.
By epsilon maybe less trivial. It's probably true also, yeah.
No. I mean, there's no, if there were such a central extension, then the second cohomology of gamma would be non-zero, and you want a specifically second cohomology.
Oh, no, but with trivial coefficient. Oh, yes, you're right. You are. Oh, yeah. Oh, yes,
Okay.
yes. You're right. Yeah.
Okay.
So it's right. Yeah, too much. Yeah. Right. Yeah. Well, then we will be non-stable, right? We need stable. I'm sorry. Yes. Okay. Let me just take. I have another 7 minutes or so. I want just to give you a glimpse where this H2 come into the game. What it has to do with the whole problem, because it looks so much non-connected to this story, and I show you how it came up. It's not like we really understood it. It suddenly came up. Okay, so assume you have a family of maps from gamma to the unitary groups UN, which are asymptotic homomorphism. Namely, each one of them is just a map. It's not homomorphism, only they are kind of converges to be homomorphism. Let me cook out of this sequence one homomorphism. How we will do it? We take U to be the direct product of all these compact group UN of C. And let's define U bar to be the so-called topological ultra product. If you know a little bit model theory of ultra product, fine. If you don't know, it's not so important. We basically take U and we divide it by the sequences of elements which converge to the identity. We have to take it converge in the sense of the ultra filter for some technical reason that I don't want to stop for that. Okay, now, but think about it. You have one sequence of homomorphisms, of asymptotic homomorphism. They are not homomorphism, but they are almost homomorphism. The difference between them and homomorphism is getting smaller and smaller. It exactly means that this sequence of homomorphism, if you look at it diagonally as a map to the direct product, once you divide it by K, which are those elements which converge to the identity, you get a single homomorphism from gamma to U mod K. So out of this infinitely many almost homomorphism, we cooked out single homomorphism from gamma to this crazy group, which is U mod K. But here is a trivial observation that I will say it, and you have to think about it for a second and convince yourself that gamma is stable if and only if for each such homomorphism phi, homomorphism that was obtained like that, which was obtained from gamma to U mod K, so we have gamma, we have homomorphism to U mod K, we have a map from U to U mod K, we want to lift it up to an homomorphism to U, which will close this diagram. The stability is exactly to a lifting up problem for this diagram. It's exactly that. It exactly means that you can correct the phi n by some maps psi n, which are nearby, and therefore modulo k, they are exactly the same. And they are homomorphisms. So you need a true homomorphism from gamma to U. What we started was only almost homomorphism from gamma to U. So now we are in the story, in the business of lifting homomorphism. Lifting homomorphism brings to the game H2. The problem is that for the general question, H2, you need basically H2 with coefficients in K. But K is a very, very non-commutative group. But here is the magic. If the norm we started with is submultiplicative, then we have a kind of, which is really for all these P between 1 and even infinity, but not true for the Hilbert-Schmidt. The norm is submultiplicative, just the norm, you know, a very technical condition. If A, the norm of AB is less or equal the norm of A times the norm of B, then we can approximate this. I need a few more minutes, and it's a bit technical, but believe me, it's a one-page proof. It's kind of similar to the situation with congruent subgroup. You know, if you take a congruent subgroup mod P divided by congruent subgroup mod P square, and the mod P square by congruent subgroup mod P cube, each one of these quotient is a billion. And you can kind of approximate the group K by a series of a billion extension. So each one is a billion, and in fact, when P equal 2, in the Frobenius case, these are Hilbert spaces. So now, and if for the other P's, you get some Banach spaces, kind of LP spaces instead of L2 spaces. Now, this vanishing of H2 is exactly the machinery to solve such lifting problem. This is classical cohomology theory. And therefore, we can use this vanishing of H2 to solve, to prove this stability, because we can lift this homomorphism. Garland theory give you almost directly the results for Hilbert spaces. For other things, and this is the work I did with Izar Oppenheim, this is theorem B, we kind of extended Izar was expert on that Banach spaces, etc. And then it's a technical work expanding Garland theory for more general Banach spaces. It's not true for totally general Banach spaces, and that's why we cannot unfortunately solve the case of P equal 1 and P infinity, even though they are submultiplicative. Okay, I think I'm just on time. Even 1 minute earlier, so but I am done. And